Pacemaker concepts. This presentation is really about the concepts or the reasons why we program the pacemaker the way we do for things like thresholds, outputs, and sensing. Two important things that we look at when programming the pacemaker are capture management and sensing. Whenever we check a patient, we really should measure a pacing threshold and then adjust the patient's outputs accordingly. This is capture management. When checking the device, we need to make sure that when we pace the heart that we capture 100% of the time. So we need to program the pacemaker output high enough that we capture the heart, but low enough that we don't unnecessarily waste battery life. The pacemaker battery only has a certain amount of charge in it, so while it would be safer for the patient to program the pacemaker at a higher voltage, it would also result in a much shorter lasting device. In order to understand why we program pacemakers the way we do and how to optimize them for each individual patient, we need to take a look at Ohm's law. If you do a quick search on the internet for Ohm's law, you would find that Ohm's law deals with the relationship between voltage and current in an ideal conductor. This relationship states that the potential difference, voltage, across an ideal conductor is proportional to the current through it. The constant of proportionality is called resistance. The equation for Ohm's law is voltage is equal to the current times the resistance. If we look at each piece of the equation, voltage is the electromotive force or potential difference expressed in volts. Current is the flow of electrical charge or electrons through a conductor. It's measured in amperes and is represented by the letter I. Resistance, the opposition to flow of current in an electrical circuit. It's measured in ohms and is represented by the letter R. Another term that we use for resistance when talking about pacemakers is impedance. A lot of people have a tendency to get current, represented by the letter I, mixed up with impedance, which is actually represented by the letter R for resistance. Some other forms of the equation for Ohm's law are current is equal to voltage divided by resistance, and resistance is equal to voltage divided by current. As the person checking the pacemaker, we're the ones that set the voltage, and we don't have any control over the resistance, so the thing that we're interested in is current. If we set the voltage and know what our impedance is, we can measure the current drain on the battery. Current is equal to voltage divided by resistance. Let's run through a couple of examples. If our voltage is programmed to 4 volts and our impedance is measured at 500 ohms, what is our current? So we just need to plug our numbers into the equation. Current is equal to voltage divided by resistance. So we take 4 volts divided by 500 ohms and we get 0.008 amperes. Typically with pacemakers, we talk about current in milliamps. So all we have to do is take the 0.008 times 1,000 and we get 8 milliamps. Now I'm going to go through these examples kind of quick, but don't worry, when I get all done with the examples, I'll put them all up beside each other so you can kind of see what I'm trying to get at. Next, let's say we have a pacemaker programmed to 2 volts. Our impedance is still 500 ohms, and what is our current? So we take 2 volts divided by 500 ohms and we get 0.004 amperes times 1,000, we get 4 milliamps. Next, let's say that we have a pacemaker programmed to 4 volts again, but this time our impedance changes. It goes down to 250 ohms. So what is our current? 4 volts divided by 250 gives us 16 milliamps. Now with that same 4 volts, let's say that our impedance went up instead of down. 4 volts divided by 1,000 ohms equals 0.004 amperes times 1,000 gives us 4 milliamps. So what's our takeaway from those examples? Well, current drain is affected by both voltage and resistance. If we look back at our examples, we can see that if we cut our voltage in half, we reduce the current drain on the battery by half, therefore making the battery last longer. We can see the same thing for resistance. If our voltage stays the same, but the impedance changes, the current drain is affected as well. From the examples, we can see that having a higher impedance will decrease the current drain and therefore will increase battery longevity. One of the best analogies that I've seen used to explain Ohm's law and how it applies to pacemakers was comparing a pacemaker system to a water tap or faucet with a hose attached to it. So I did a quick search and found a presentation from Medtronic with a couple of great pictures showing the analogy. In some examples, instead of a pipe coming up from the ground with a tap on it, there's a bucket or a tank of water with a tap and then a hose connected to the tap. So here's a connection. Water pressure in the system is analogous to voltage, providing the force to move the current. The water would represent the current. So when we open up the tap, it's like turning up the voltage. Lots of water flows out, and you have a high current drain. But if we close that tap most of the way, the tap, or the voltage, is turned low, so there's little flow or a low current drain. The thing I kind of like about the example with a water tank versus just a pipe coming out of the ground is the water tank sort of represents the battery capacity. All right. So as you open up the tap, the water flows out, draining the tank. This is also very similar to when we turn the voltage up on a pacemaker. We're allowing that current to flow, and eventually we're going to drain the tank or the battery. So that kind of explains voltage and current flow. But there's another component to it too, resistance. Normal resistance in this case is the friction caused by the hose and the nozzle at the end. The larger the diameter of the hose, the less resistance. More water is obviously going to flow out of a fire hose compared to a little garden hose. This hose with a normal resistance is analogous to a normal functioning pacemaker lead. Here we see a normal pacemaker lead. Leads typically have a silicone or a polyurethane or maybe some combination of the two outer insulation. Running down that insulation are a couple of conductor wires. One wire running down to the tip, which is the cathode and is negative, and another wire running down to the anode, which is positive. When we pace, that current travels down the conductor, out the cathode, and back into the anode, hopefully capturing cardiac tissue in between the two. When we measure the impedance of a good functioning lead, we'll typically get an impedance of 300 ohms to 1500 ohms. Every lead's a little different, and they're manufactured to have a different normal impedance, but typically 300 to 1500 will usually suggest that that lead is normal or functioning properly. But what happens to a lead impedance if the lead is damaged? If we look back at this image and take a closer look at the hose in the middle, we can see that the hose has developed some cracks or cuts in the side of the hose, allowing water to spill out the sides. Because of this extra water spilling out, the hose has a high total current flow as a result of low resistance. The resistance of this hose is low because there's more areas for the water to escape from. This is very similar to when we have an insulation failure. If you look at the arrow, you can see that there's a section of the lead that's missing its insulation. It's possible that over time a crack could form in the insulation of the lead. It's also possible for the lead to get some sort of scrape or abrasion on it, possibly from implant. In the case of an insulation failure, we said they would have a low resistance. If the insulation failure is bad enough, the impedance measurement will usually be less than 200 ohms. Now let's turn our attention to the bottom hose. The bottom hose has a knot tied in it, representing a high resistance, resulting in a low current flow. This would be very similar to if we had a conductor fracture. Now, instead of the problem being with the outer insulation of the lead, the problem is actually on the inside with the conductors. At the arrow you can see a definite break in the conductors going down to the tip. When we have a conductor failure, we'll typically have an impedance of greater than 2000 ohms. If you ever get an impedance of greater than 2000, try retesting the impedance in unipolar. If the impedance goes back to a normal measurement, it means that the problem is most likely with the anode conductor. When we pace in unipolar, we take the anode ring out of the equation. The pacemaker becomes the anode, and we pace from the cathode, the tip, to the pacemaker can. If the impedance measurement goes back to normal, it means that the problem is most likely only with the anode conductor. So to be on the safe side, the patient should get a new lead. If one conductor has failed, the other one's probably not far behind. If the impedance still remains high when retested in unipolar, it means that there is a problem with the cathode or both the anode and the cathode conductor wire. Another cause of high impedance can be a bad connection in the pacemaker header block, possibly a loose set screw. So to review, a normal lead impedance is typically between 300 ohms and 1500 ohms. Remember, every lead is different. What is a normal lead impedance measurement for one lead may not be normal for a different lead. Some leads are specifically designed to have a high impedance. Each lead has a manufactured recommended normal impedance range. If you suspect a lead problem, you should always find out what the normal lead impedance measurement range is for that specific lead. If we have an impedance of greater than 2000 ohms, this would suggest that we have a possible lead fracture. If we have an impedance of less than 200 ohms, this would suggest that we have a possible insulation failure. Threshold: the minimum amount of electrical energy needed to consistently capture the heart outside of the heart's refractory period. It may also be referred to as stimulation threshold or pacing threshold. There are two components to a threshold: amplitude, which is the voltage, and pulse width, which is the amount of time that the voltage is delivered. When the amplitude and pulse width are stated together, it's known as the output. Safety margin is programming the pacemaker at a high enough output above the threshold to make sure that we capture the heart consistently. If the patient's threshold fluctuates and goes up higher, we want to make sure that we have enough safety margin so that we always capture the heart when the patient is out in the real world. In order to determine a good safety margin, we first need to talk about the relationship between voltage and pulse width when programming an output. Output. Output is stated as a blank number of volts at a blank number of milliseconds. If we were to draw out the output, it would look something like this. The vertical portion is the voltage, and it represents our amplitude. The horizontal portion is the pulse width, and is stated in milliseconds. So when we're talking about output, we're really talking about the amount of voltage delivered over time. The reason why we have a dip in the voltage over time is because the pacemaker can't maintain a constant voltage for that amount of time. If we start out pacing at 3 volts, it'll probably end up at about 2.7 or 2.8 volts. Another thing that we want to talk about is the strength duration curve. If you were to measure someone's threshold with multiple voltages and multiple pulse widths, you could plot them all out on a graph and it would look something like this. Once again, we have the voltage on the vertical axis and the pulse width on the horizontal axis. Let's say we had a patient and we started measuring thresholds, and we checked the threshold and we got 1 volt at 0.6 milliseconds. If we plotted that point and then retook another threshold and we ended up getting something like 2 volts at 0.3 milliseconds and then plotted that point, we could continue on measuring lots of different thresholds, plotting those points, and eventually if we connected those points, we'd get this curved line. It's a bit easier to see if we add some color. Basically what this curve is showing you is if we program a value that lands in the green, we should have capture. And if we program a value that lands in the brown, we're going to have a non-capture. For example, if we program the pacemaker to 2 volts at 0.5 milliseconds, we should have capture. But if we program the pacemaker to 1 volt at 0.5 milliseconds, we're not going to capture. An interesting thing that the strength duration curve is showing us is that if we increase our voltage, we could probably decrease our pulse width and still capture the heart. And vice versa. If we increase our pulse width, we could probably decrease the voltage and still safely capture the heart. From the strength duration curve, we learned that sometimes if we use a smaller voltage but a longer pulse width, we can achieve a good threshold as well. If we were to draw it out, it would look something like this. We have a smaller voltage, but it's being delivered over a longer period of time. So is it better to use a smaller voltage or a shorter pulse width? Well, to find that out, we really have to look at the energy equation. Energy equals voltage squared times time divided by resistance. Because our voltage is squared, if we double our voltage, we end up using 4 times as much energy. But since our time isn't squared, if we double our time, we only end up doubling our energy. Let's run through a couple of examples. Let's say we have a pacemaker programmed to 2.5 volts at 0.5 milliseconds. So we just plug those numbers into the equation and we get 2.5 volts squared times 0.05 milliseconds divided by 500 ohms, which gives us 0.00625 joules, or if we take it times 1,000, we get 6.25 microjoules. Next, if we double our voltage, we would have 5 volts squared times 0.05 milliseconds divided by 500 ohms, and we'd get 25 microjoules. Now, if we go back to 2.5 volts, but this time double our pulse width, we would have 2.5 volts squared times 1 millisecond divided by 500 ohms, giving us 12.5 microjoules. So if we look between our first two examples, where we doubled the voltage, we ended up quadrupling the amount of energy used. But when we doubled our pulse width, we only doubled our energy being used. So when programming a device, is it better to use a higher voltage or a longer pulse width? Well, it really depends upon our threshold and personal preference for the physician. If we go back to our safety margin, the industry standard is typically 2 times the voltage safety margin or 3 times the pulse width safety margin. So for example, if we measure a threshold and get 1 volt at 0.5 milliseconds, we want to be sure to program our voltage of 2 volts at 0.5 milliseconds, or if we're going for a pulse width safety margin, we'd want to have 1.0 volts at 1.5 milliseconds, 2 times the voltage or 3 times the pulse width. If we had a threshold of 2 volts at 0.4 milliseconds, we'd want to have a voltage of at least 4 volts at 0.4 milliseconds, or at least 2 volts at 1.2 milliseconds. If we measured a threshold of 0.8 volts at 0.5 milliseconds, we'd want to have a voltage of at least 1.6 volts at 0.5 milliseconds, or 0.8 volts at 1.5 milliseconds pulse width. Next, we're going to talk about sensing. Sensing is the ability of the pacemaker to see when intrinsic depolarization is occurring, and it's measured in millivolts. If we look at the bottom, we can see a couple of EKG beats. If we were to draw a sensing grid over these beats, with the baseline being 0, it would look something like this. Let's say that the pacemaker is programmed to a sensitivity level of 4 millivolts. This means that anything under 4 millivolts, the pacemaker won't see. It's going to completely ignore it. If we were to reprogram the pacemaker to a new sensitivity of 6 millivolts, all the pacemaker would be able to see is R wave. Everything below 6 millivolts would not be seen. One thing that can be a little confusing with regards to sensing is when programming from one sensitivity value to a new value, it has an inverse effect on the sensitivity. For example, if a physician says, "I want you to decrease the sensitivity on the patient's ventricular lead," you would actually have to program a larger sensitivity number. If we want to decrease the sensitivity of the pacemaker or how much the pacemaker sees, we have to increase the sensitivity setting. And if we want to increase the sensitivity or make it so that the pacemaker can see more, we have to decrease our sensitivity setting. Let's look back at our example. If the ventricular lead is set to a sensitivity of 4 millivolts, it means that the pacemaker will not see any signals under 4 millivolts. Anything above 4 millivolts and the pacemaker will see it. So here we can see that the pacemaker is going to see that we have an R wave and a T wave. Because of our ventricular refractory period timing cycle, pacemakers are pretty good at filtering out T waves. It is possible that if a patient has a long enough QT interval, that some T waves will be oversensed. If that is happening, we want to make this pacemaker less sensitive so that we don't see that T wave anymore. So in order to make the pacemaker less sensitive and stop oversensing the T wave, we need to program a higher sensitivity value. So if we go from 4 millivolts to 6 millivolts, now the pacemaker only sees the R wave and no longer can see the T wave. Think of the sensitivity setting as a threshold. A signal has to cross that threshold in order for it to be sensed. So to review one last time, if we want to decrease the sensitivity, or we want the pacemaker to see less, we need to increase the sensitivity setting. And if we want to increase the sensitivity, meaning we want the pacemaker to see more, we need to decrease the sensitivity setting. Safety margin. So just like thresholds, we want to have a safety margin when it comes to sensing as well. The accepted industry standard is a 2x safety margin when it comes to sensing. What this means is we want to program a sensitivity setting of half of what our measured P wave and R wave are. So in the atrium, we want to program half of the measured P wave, and in the ventricle, half of the measured R wave. For example, if we have a measured P wave of 3 millivolts, we would want to program our sensitivity setting to at least 1.5 millivolts or less. If we have a measured R wave of 8 millivolts, we'd want to program our ventricular sensitivity to 4 millivolts or less. So anyways, that's all I have for pacemaker concepts. I hope that it was helpful.